Hey guys, in this video I'm going to do a solution to the half-atwood machine whiteboard that we did in class last time. So recall that the half-atwood machine is hanging mass right here, a sliding mass right here, a pulley, and they're connected by a string. We haven't really talked about pulleys and strings very much. For the moment, you know what a pulley is. This pulley is massless, there's no friction on it, no energy is lost through the pulley, and the string really just changes the direction of an applied force. So any force applied at this end of the string is transferred along the string. We're going to talk a lot more about strings later in the semester, but for the moment, this is enough. And so the question is, if this mass falls at height h, how fast is this moving if it falls 73 centimeters? So first I'm going to do part A. So we haven't really talked about these kinds of diagrams. These are called interaction diagrams. I think it's useful to organize your thoughts. It's not always useful for a problem. In this case I think it was, so I asked you to do it. So I'll do one. It should consist of all objects and interactions going on. So how many objects do I want in my system? Clearly I have a mass here, I have a mass here, and they're both interacting with the Earth. So I need those three objects at least. M1 and M2 are interacting through the string, and M1 and M2 are both individually acting on the Earth. Of course, in principle, M1 and M2 are actually interacting gravitationally as well, but that effect is so small we're going to neglect it. And so this is going to be my system. I'm going to put a dotted line around it to indicate that it's my system. So I should make one more note, and that is that there is one additional interaction which I did not take into account, and that's the interaction between M2 and the ramp. So why isn't M2 falling to the ground due to the interaction with the Earth? Well, the ramp is pushing up on it, so that is an interaction. It's just a question of how I want that interaction to take into place in my system. So just to be safe, I'm going to put that inside my system in the following way, like that. So I have a ramp which is interacting with M2. But we have to know the character of the interaction. The interaction occurs through a frictionless surface, so this is infinitely slippery. So although the ramp might be pushing upwards on the block to prevent it from falling downwards, since it's not going to be acting in this direction at all, it's not going to be changing the velocity of M2. This is a conservation of energy problem. It's not going to do anything to M2. So that's why I put it in blue. It's going to be there, but it's not going to have any effect. Okay, so now let's go on to answering part B of this question. Okay, so what is the speed of the sliding block when the hanging mass falls 73 centimeters? We want to start off by writing our master equation. EF minus EI equals 0. The change in energy is 0. We have sources of energy, kinetic and potential, so let's just start by writing out as if we had both final and initial kinetic and potential energies. Okay, so now I'm going to replace kinetic energy, 1/2 mv squared, and potential energy, mgh, with the variables found in my problem. Immediately, I am confronted with something, which is that this is supposed to be 1/2 mv squared, but I need to know what mass I'm talking about. The velocity, this is the final velocity of the system, that makes sense, but the mass has to be all the mass that moves, because this is kinetic energy, it's the energy of motion. All the mass that moves is the entire mass of the system, the mass of both blocks. So, the final kinetic energy should look like the following. Like that, 1/2 m1 plus m2 times the quantity vf squared. That's what the initial kinetic energy is going to look like too, but first we need to deal with what the final potential is going to be. So if you recall, the potential, the mass falls 73 centimeters. I can choose where the potential for gravity is going to be 0. I'm going to pick at the bottom. So I'm going to say that at the bottom the potential is 0, at the top the potential is mg times that height. So I can just put in plus 0 because the final potential energy is going to be 0, minus 1/2 m1 plus m2 v initial squared, plus m, and which m is changing in potential. The potential is only changing because the hanging mass is moving, so this is only m1 g times h, where I'm using h to be 73 centimeters. Set that equals 0. So now that I've done this step, then my next job is to solve this equation. But of course I should be able to count the known and unknown variables and make sure that all these variables are either known or I can solve for them. So M1 and M2, all the masses in fact, those are all given to me. I'm looking for the final velocity, so this is okay. G is a constant, h I've been given 73. but I still have a VI here. Of course, this thing was intended to be at rest. So I can set that VI to be 0, and so the next line of my algebraic solution will be that, and from here I can just do some algebra to isolate VF by itself. Alright, so here's my final answer. I can put in the numbers if you like, and if I put in the numbers I end up with something like 3.68 meters per second as the velocity of the system after it falls 73 centimeters. So this solution was fairly straightforward, but the trick is to make sure that you understand what goes into the kinetic and potential energies. That means you want to know what mass is moving and what velocity they're moving at, and you need to set the gravitational potential to be 0 at a given place, and figure out which mass is actually falling. So this has a little bit of a trick in the terms of where the masses go, but besides that, it's a pretty straightforward application of conservation of energy. Okay, so that's the video. Thank you guys for watching, and I'll see you guys next class.